Hello everyone, this is Professor Keene. We have been discussing Chapter 6 in A Student's Guide to the Great Physics texts, where Galileo is discussing beam breaking. He is using the law of the lever to give us a better understanding of the conditions under which a beam that is extending from a wall horizontally, under what conditions they will tend to break or not tend to break. In the first two propositions, what Galileo did was talk about how the shape and orientation of the beam causes it to resist fracture when a transverse force is applied to the end of the beam. In the third proposition, he talks about how it tends to break because of its own weight acting on it. Now we want to talk about the fourth proposition. So in proposition 4, he returns to the question of not how it tends to break under its own weight, but how the diameter of the beam and the length of the beam affect the amount of transverse force that is required to break the beam. So this is from page 80 in A Student's Guide to the Great Physics texts. And the question that's being asked is, for a beam projecting from a wall horizontally, how does the resistance to transverse fracture by a force Ft, F sub t, increase with the length, increase or decrease with two factors, the length L and the diameter d of the beam. Okay? So what he's essentially asking is, if you make the beam of a certain diameter, d, that's the thickness of the beam, and if you make the beam of a certain length, and you ask how much force does it take to break it, what happens as you make it longer and what happens as you make it thicker? How does the force that's required to break it change? So what we're going to do is we are going to consider two separate situations. So we're going to consider two beams of the same material, that's important, but different diameters and lengths. Different diameters and different lengths. And we're going to ask, how does the transverse force required to break them, how are those different? So let me draw two pictures. Let's draw first beam, we'll call this beam A, sticking out of a wall. I'm not going to draw the part that's inside of the wall. Okay? And let's suppose that this beam has a resistance to a longitudinal resistance R sub A, and this one has a length L sub A, and this one has a diameter D sub A. And again, it's a square cross-sectional beam, so it's got a height of dA and a depth of dA. And let's suppose that you apply a transverse force to it, call that F sub A, to the end of the beam. And now I'm going to draw a second beam that has a different diameter and a different length. And this one has a longitudinal resistance R sub B and a length L sub B and a diameter D sub B. And then we can ask how much force F sub B does it take to break that one? And what we're really asking is, how does F sub A compare to F sub B? Okay, now remember, the conditions for beam A or beam B to break is for the breaking moment to be exceeding the resisting or supporting moment. So let's remember that we have a fulcrum right here on each of the beams, and this transverse force is applying a torque that's trying to rotate it downwards, and this longitudinal resistance is applying a torque that's trying to hold it up. And likewise with this beam, this transverse force is applying a torque or a moment that's trying to rotate it and make it fall down, and this resistance is applying a torque or a moment that's trying to hold it up. If these two beams A and B are both on the verge of breaking, then their breaking moments exactly equal their supporting moments. So if you were to increase the breaking moment just a touch more, then each of them would shatter. Okay? So what is the condition, the mathematical condition that holds such that the breaking moment of A is exactly equal to the supporting moment of A? Okay, so let's consider case A. Well, the breaking moment is given by force A times the length of A. Remember, that's that force times the lever arm. And we're saying that it's on the verge of breaking, so that means that that is exactly equal to R sub A times D sub A over 2, right? Because this is the lever arm that the resistance, longitudinal resistance, is acting with in order to support it. And for beam B, we know likewise that the transverse force F sub B times the lever arm L sub B has to be exactly equal to R sub B times D sub B over 2. If that force is increased a little bit more, then it will break. If this force is increased a little bit more, then it will break. Okay? And now we want to find the ratio. We'll find the ratio, actually, because we want to determine how these relate to one another. How big does FB have to be compared to FA? We're going to have to find these. Well, we can just solve for FB in this formula by moving LB to the denominator. So that will be R sub B times D sub B over 2L sub B. Again, I basically moved this to the denominator over there. And likewise, I'm going to move the L sub A to the denominator over there. So FA is going to be R sub A times D sub A over 2L sub A. Okay? So we want to find that ratio. Now, this is these resistances right here are not going to be the same. Why not? Because this beam has, although it's the same material, the same substance, these two beams have different cross-sectional areas. And as I mentioned before, the longitudinal resistance, I think this was about 2 lectures ago, I talked about how the longitudinal resistance, that is how easy it is to break when applying a longitudinal force to it, that depends on the cross-sectional area of the beam. So you just might want to remember, if you have some beam like this and you are trying to apply a longitudinal force to it, the force you have to apply to it in order to break it in this way depends on the cross-sectional area of the beam. And the biggest longitudinal force you can apply before it breaks, that's just equal to the longitudinal resistance R. So remember that the longitudinal resistance is proportional to the area or the cross-sectional area of the beam. If you're having trouble remembering why that might be, just think about if you take a spaghetti noodle like this and you want to pull it and snap it. If you have twice as many spaghetti noodles, you take a bundle of 2 of them, it's going to be twice as hard to snap it because they have twice the cross-sectional area. Or 10 spaghetti noodles, it's going to take 10 times as much force because they have 10 times the cross-sectional area. Generally speaking, the longitudinal resistance is proportional to the area. Why is that important? Because here we have a ratio of these longitudinal resistances. So R sub B over R sub A is going to be equal to the area of beam B divided by the area, the cross-sectional area of beam A. And for a square cross-sectional area, or in fact, as long as these are both square or both circular or both the same shape, those ratio of the areas is going to go as the diameters squared. So in other words, there's a factor of diameter hiding in this ratio of the longitudinal resistances. So let's make that latent dependency on diameter manifest or explicit. So RB over RA is the same thing as DB over DA squared. And we've still got another DB in the numerator and a DA in the denominator. And then the 2's, are going to cancel out. And since this is in the denominator, we'll put the LB there. And this is in the denominator of the denominator. So let's put that in the numerator, like this. And so we can simplify now and just say that the ratio of the forces required to break beam B compared to beam A goes as the diameter of B cubed over the diameter of A cubed times the inverse ratio of the lengths, LA over LB. This right here is what Galileo arrives at. This is the result of his proposition 4. In other words, and this is, by the way, on page 83, he gets to this, and what he's saying essentially is the force it takes to break, the transverse force that it takes to break a beam, is proportional to the diameter cubed divided by the length. So essentially what he's saying is we actually arrived at this result, the inverse dependence on the length, in I think proposition 1. But this is going further. It's saying that if you double the length, it's going to take half the transverse force. We knew that already. But it's saying by doubling the diameter, it's going to take 8 times the transverse force, because 2 times 2 times 2 is 8. So as you make it longer, it gets weaker, it's easier to break it. But as you make it thicker, it gets much stronger. Okay, so why don't we stop there? This is proposition, by the way, this is proposition 4. If I remember correctly, this is proposition 4 and proposition 5 combined. I think I've combined these into one statement. Okay, we'll continue next time.